CicuDevices.
Impella. Impella components. Impella CP from tip to toe, Part 5. The Purge System. This video is a continuation of our previous video, Impella CP Components Part 4. The link can be found in the description. For more insights on Impella device, we recommend you to visit our Impella Guide playlist on the CicuDevices channel. The purge system of the Impella device is a critical safety and performance component, designed mainly to establish a pressure-mediated fluid barrier between the bloodstream and the motor of the microaxial pump, thereby preventing blood ingress and protecting the motor from damage. In parallel, the purge fluid fills the motor housing to create a thin lubricating film around the bearings, ensuring smooth mechanical operation and long-term device reliability. Functionally, the Impella purge system operates as a pressurized fluid circuit that continuously delivers a dextrose-based solution through dedicated tubing and control hardware. By maintaining a controlled counterflow pressure at the motor housing, the system minimizes blood exposure to internal components, reducing the risk of device-related thrombosis and hemolysis while stable left ventricular support is provided. The Impella purge system consists of a set of integrated components designed to ensure stable purge flow and pressure at the motor housing. These elements include the purge fluid bag, the purge cassette, the purge tubing, the purge filter, the purge pressure reservoir, and the check valve. Thus, the purge fluid flows through the circuit, circulates around the motor shaft, and finally exits through a small gap located between the motor housing and the impeller, creating a continuous barrier that prevents blood from entering the motor. Understanding each component of this circuit, starting at the purge bag and ending at the side arm on the Impella plug, is essential for safe bedside management and for troubleshooting alarms related to purge flow or pressure. At the beginning of the circuit system lies the purge fluid bag, which contains the purge solution. In the initial instructions for use of the Impella CP device, the recommended purge solution consisted of 20% dextrose to achieve higher viscosity, combined with heparin at concentrations ranging from 25 to 50 international units per milliliter. Over time, the safety of using 5% dextrose was demonstrated, allowing a transition to lower viscosity solutions without compromising device performance. Subsequently, the use of sodium bicarbonate instead of heparin was shown to be a viable option in patients with heparin-induced thrombocytopenia or severe coagulopathy. Of note, only dextrose-based solutions must be used as purge fluid, and saline should never be administered, as saline solutions increase the risk of crystallization within the motor housing. Sodium bicarbonate does not exert a direct anticoagulant mechanism comparable to heparin. Its protective role in Impella purge solutions using bicarbonate-based purge solution is primarily related to the maintenance of a stable alkaline pH of approximately 7.8 to 8.0. This alkaline environment reduces local platelet aggregation and thrombus formation within the motor housing. In vitro studies further suggest that bicarbonate at purge concentrations of 25 milliequivalents per liter may minimally modulate local thrombin and factor XA activity through pH elevation. In addition, bicarbonate helps preserve the stability of plasma proteins, such as albumin, and reduces the formation of protein aggregates and fragments, thereby lowering the propensity for thrombus formation within the narrow flow paths of the Impella motor. As a result, the currently recommended purge fluid composition may consist of either 5% dextrose with heparin at a concentration of 25 or 50 international units per milliliter, or alternatively 5% dextrose with sodium bicarbonate at a concentration of 25 milliequivalents per liter. Accordingly, a possible preparation of the purge fluid may be as follows: 500 milliliters of 5% dextrose with 12 thousandths and 500 units of heparin, or alternatively 500 milliliters of 5% dextrose with 12.5 milliequivalents of sodium bicarbonate. The purge fluid bag is hung above the automated Impella controller, and it is connected via a purge fluid spike, which pierces the bag to draw fluid, and a supply line that carries fluid from the bag to the internal mechanism of the cassette. The core of the system is the Purge Cassette, a single-use accessory that mounts on the front of the controller. Externally, the Purge Cassette has the shape of a quadrangular-based prism. On its posterior surface, it features an opening designed to engage with the console rotor, allowing correct mechanical coupling and fluidic actuation. Internally, the cassette features an internal channel architecture that guides purge fluid flow through the cassette, along with a syringe-like embolus mechanism. The Purge Cassette of the Impella device incorporates a rack-and-pinion piston pump mechanism integrated with two unidirectional check valves to precisely regulate purge flow and pressure within the system. This electromechanically driven positive displacement pump features a linear piston coupled to a rack gear, which is actuated by a pinion driven by the stepper motor in the controller. Next, the purge pressure disc is a key internal component of the Impella Purge System, designed to monitor the pressure of the purge fluid delivered to the motor housing. By responding to changes in purge line pressure, it allows the console to continuously adjust purge flow in order to maintain a protective pressure barrier within the motor housing. Structurally, the purge pressure disc consists of a flexible diaphragm and an interface region that couples mechanical deformation to the internal pressure sensing system of the console. This way, the purge fluid does not come into direct contact with electronic components. In terms of operating principle, purge fluid is delivered from the console into the catheter under variable flow rates. As purge pressure rises or falls, the purge pressure disc deforms proportionally. This deformation is detected by the console's sensing mechanism, which automatically increases or decreases purge flow to maintain pressure within the desired range. This process is fully automated and continuously active during device operation. Target purge pressures are typically maintained between 300 and 600 millimeters of mercury. Operating within this range ensures effective motor protection. Continuous monitoring of purge pressure via the purge pressure disc is therefore essential for safe, stable, and reliable Impella support. From the cassette, purge tubing carries the fluid onward toward the catheter. The purge tubing is a thin plastic tubing that connects the purge cassette to the components of the purge unit. Of note, in its early designs, the purge tubing incorporated a Y-shaped extension that connected both the arterial lumen and the purge lumen. Beginning with the Smart Assist models, this Y extension was required to be discarded during the initial system setup. In the most recent design, the purge tubing no longer includes the Y extension and instead features a modular configuration. This design allows the use of a 3-meter tubing segment for the Impella CP, or the removal of part of the tubing to achieve a shortened length of approximately 20 centimeters for use with the second-generation Impella 5.5. You can find more information in our previous video on the second-generation Impella 5.5. The link is available in the description. The purge tubing must be attached to the white cable by securing it into the clips along the cable as shown in the video, to maintain an organized and tangle-free layout from the insertion site to the console. We recommend watching our video on the channel about nursing care for the Impella CP to get more information about these aspects of care. The tubing terminates in a yellow lure connector or yellow lure lock, which interfaces with the corresponding yellow lure on the Impella catheter. This last component is referred to as the yellow check valve. as it incorporates a valve mechanism that enforces unidirectional flow of the purge solution from the console toward the catheter, thereby preventing any retrograde flow of purge fluid during disconnections. The Impella CP purge unit comprises an integrated filter reservoir check valve assembly. It was redesigned as a single, unified component to minimize the risk of tubing kinking, disconnection, or structural fracture within the purge system. This integrated design improves mechanical stability and enhances overall system reliability during clinical use. At its proximal end, the purge unit incorporates an additional yellow check valve. Distal to this valve, the purge unit includes the purge pressure reservoir, an elastomeric membrane designed to temporarily maintain purge pressure for approximately 1 to 2 minutes during brief purge system disconnections. This feature helps preserve the protective pressure barrier within the motor housing and reduces the risk of blood ingress during handling or troubleshooting. A 0.2 micron filter is incorporated into the purge line to prevent particulate contamination and to maintain system sterility, which is critical for reducing infection risk and ensuring long-term device performance and durability. For mechanical stabilization, the purge unit is equipped with a connector clip that secures it to the white catheter cable, helping maintain proper alignment and further preventing kinking. Finally, the purge unit connects to the red hub via the side arm, a reinforced segment specifically designed to resist kinking and mechanical stress, thereby ensuring uninterrupted purge flow and consistent system function. From the side arm, the purge tubing enters the red hub, where it is routed toward the Impella catheter itself. Within the catheter, the purge solution travels through the internal lumen until it reaches the motor housing. Inside the motor housing, the purge fluid flows around the rotor until it reaches the gap, where it creates a barrier that prevents blood from entering the motor housing. Continues on Part 6.
If you've enjoyed our video, please press the like button and subscribe to support us so we can continue creating quality content like this.